1.1 functions and their representations. This will be the introduction to calculus. I have made a few calculus videos in the past, but this is going to be the actual introduction. So what are functions? Now it's something that takes an input and yields an output. So it's like a machine. Think of it like where you put potatoes into something and it gives you a baked potato. And how that machine deals with each potato is depending on its size, the origin, the background, the nature of that number. So think of each potato kind of like a number going into like a machine that transforms it into like a baked potato or a different type of potato. And that's kind of the easy way to think about it. So only one output exists from one input. That means if you put one potato in, you can't either get a baked potato or mashed potatoes. You can only get one. I don't know if mashed potatoes, you can make them with baked potatoes, but the point is that you can't get two separate things. Once you put one input in, you will always get the same output. So f of x, which is this notation right here, the f doesn't matter. You can say g of x, h of x. Those are like the three most common ones I've seen, probably because a, b, c, d, e, f, g, h. I do sometimes see like p of x, which is polynomial. When you put the input into a function, you get a result back, and that's f of x. We deal with this all the time. Take a circle's area. Area equals pi r squared. Pi is constant, so the only changing variable is r, which modifies the area. So the input would be r. So depending on how big the radius is, you'll get a area as depending on how big the radius is, you'll get an even bigger area because it's multiplied. Actually, that's not necessarily true in the case of like 0.5. But anyways, the point is that there's an input, which is the radius, and it gives you an output, the same output each time, depending on the same input each time. So what is the domain and range? Domain and is simply the possible inputs in a function. Let's take the function f of x equals x square root x. The domain is 0 to infinity, since negative numbers don't have a square root. Theoretically, they do in... Wait. No, they do in higher level mathematics. Well, not higher. There's imaginary numbers, but there isn't really a foolproof arithmetic way to solve for the domain. So just use logic and intuition. So what do I mean by that? Let's go over here. I'm sorry, these are vectors actually. So we have square root x plus 2. And this is what I noticed. There's not really a foolproof way to do it. I think I've searched it up and no, it's all intuition. You can look at a graphing calculator, I guess, which graphs every possible method. But I don't think there's like a proof or like a foolproof way to do it. So if anybody wants to discover that, they can. So let's look at the domain of this function. Well, negative 2 makes it the smallest that this thing can be, and it can't go beyond 0. So if it was negative 3, then we would have an undefined function because it would give an imaginary number, which is not real. So we can say the domain is limited from, and you can use set builder notation, which is just x is equal to all real numbers. You always put this, and then you just put the argument right after. So x has to be between negative 2, I guess it can be negative 2 and infinity. Wait, we have this one. X also cannot be equal to 2, because if it is, it makes it 0, and it's an indeterminate form. So anything that makes it indeterminate or impossible is in the domain. Now, what is the range? Now, range is simply, and I didn't write this down in the notes, so I'm just going to tell you now. A range is simply all the possible outputs. So let's look at x. What's the range of this? It's infinity and negative infinity, because if you put infinity in here, you'll get infinity back. So we get negative infinity, infinity as the range. And I guess the way to test the range would be to test every single point in the domain, which is not possible because intervals have infinite points. But the point is that I guess you can look at the maximum and minimum of a function to find the range. The absolute maximum and minimum, not the relative. So yeah, that's the logic behind that. So what are piecewise functions? Piecewise functions are things that are defined on a certain interval. This is really simple. I used to stress a lot about this, but I mean, actually not a lot. I guess it was when I didn't pay attention in class. So here's negative 5, 5. We have negative 5 and 5. And I probably should have made these this number bigger. So if x is greater than 0, it's x plus 3. So if it's 3, that's 4 probably. So if it's 3, then we'll have an x function here. And notice that's only if x is greater than 0. If x is less than 0, it's negative x, which looks like that. So this would be the function for that. And that's the logic behind it. There's literally nothing special. It just defines the function on 2 different intervals. So even and odd functions. This is really cool, actually. And last year just took this advice, but I didn't really know how it worked, but it's really common sense. So I'll just use an example here, and we'll use a very simple one. We'll use a first degree or second degree polynomial, x squared. Now, if we look at the graph of x squared, it looks like this. It's even around the y-axis, which means that it's an even function, or it's symmetric around the y-axis, which means it's an even function. What does that mean? Well, it's even, it's symmetric around the y-axis, right? So that means the inputs before and after must yield the same value, which is the logic behind this. If you only flip the sign, if you just flip the sign of this side, if you flip the x sign of this side, you'll get this function. So what does that mean? Well, let's input negative x into the function, and we get negative x squared is, this should probably be on the right side to make it a little bit consistent with the notation, x squared. What is negative x squared? No matter what, that's x squared. So these are the exact same functions. So that means on the negative x side, no matter what the value is, even if it's negative, numerically it's the same as the right side, meaning that they will yield the same y value and be symmetric around the x-axis because each input yields the same y value as the right side. So that's the logic behind that. And the last one, increasing and decreasing intervals. This is quite easy. You can look at the formal definition if you want. If the function increases as x increases, it increases. If it's decreasing as x increases, it is decreasing. That's a simple way. This is if x of 2, which means if the second output is greater than the first output, while the second input is greater than the first input, it's increasing. So on and so forth. You can use function notation, but I'm just going to explain it. So let's say we have a function y equals x, and we'll set this as 10, negative 10, and we'll do negative 10 and 10 here. So we just have that. Now let's take an interval, and everyone should know that with x it's always increasing because as you increase x you get a higher function. But let's just take this interval right here between these 2 points, and that looks around 4 and this looks around 2. So what's here? It's going to be 4 and 2, which doesn't look consistent with the graph, but it's okay. So since this output is greater than this input, while this output is also, why am I subtracting? Since this output is greater as x is increasing to 4, so these are the output and input, they're increasing. If this was decreasing, then the output here would be smaller, like around this area here, as x is increasing, and that's what that means. So just take this notation as is, literally. You can just plug in points here to figure this out, and that's the logic behind 1.1 calculus.